new updated syllabus calendar. So we're going to talk about rational functions and their graphs today. Okay. And your quiz 5 was a take-home quiz, is due today. Just put it in your folder before you go. Monday, we're going to do 2 lessons on Monday, okay? 31 and 32. Now, I think that I can fit them both into our hour and 10-minute class, but I'm going to stay here until they're both done, right? So if you need to go, you need to go, and you'll just be held responsible for watching whatever video I create and doing the activities on your own, okay? But if you want to stay, I'll be doing the whole lesson on Monday. 32 and 33, yep. Like I said, I'm going to try to fit them in both in the hour and 10-minute class. I might go a little bit longer than that. So if you can stay, try to stay. Otherwise, you'll be responsible for whatever you miss after you go. And then that will make up for the fact that I'm canceling class on Wednesday so that you can have one more day, especially since this is like the last class meeting of the day on Wednesday. I know some people might want to hit the road, get to traveling, so Wednesday is canceled. And then Monday is going to be your new due date for Project 3. It was supposed to be Wednesday, but since we won't be having class, I pushed it back until the next time I see you, which is Monday the 30th. Okay. Any questions? All right. So we're going to talk more about rational functions today. So last class, we studied the behavior of 2 new parent functions, 1 over x and 1 over x squared. We can graph many rational functions by just transforming one of these parents, right? Shifting right, left, up, down, stretching vertically or horizontally. Okay. Both of these parent functions have a vertical asymptote at a value of x that is excluded from the domain. So for each function, x equals 0 is not in the domain. Okay. So which is which? Which parent? One of these is 1 over x and one is 1 over x squared. The first one is 1 over x, yeah. So this one is f of x equals 1 over x. And this one is, we'll call this g of x, 1 over x squared. Good. So in general, if you have a rational function, oops, missing a letter there, r of x, right, which is p of x over q of x, you know, a polynomial over a polynomial, how do you find vertical asymptotes? What did we do last class to try to find out where the function was undefined? Yeah, it has to do with the domain. And what do you do to find the domain? What would make the denominator of the fraction a 0, right? So we set q of x, which is the denominator, equal to 0. That's how you find your vertical asymptotes. All right, so I'm looking for equations of vertical asymptotes in each of these 3 graphs. First graph, do you see any vertical lines in there that the function approaches but never crosses? No, no vertical asymptotes. Okay. In the next graph, we've got this pink line. What is the equation of that vertical asymptote that the graph approaches but never touches or crosses? X equals 2. Great. And then in my next one, I have a vertical asymptote at -2 and at 2. So x equals -2, x equals 2. Can the graph of a rational function intersect a vertical asymptote? Can it ever touch or cross a vertical asymptote? No. Oh, then it doesn't actually touch it then. If there's a, it does cross it, yeah, but I guess it doesn't intersect it, yeah. Good. All right, and how do we indicate a vertical asymptote on a graph? We draw it with a dotted line. Yep. Good. Okay, so here I've got a function, x squared minus 9 over x plus 3. What x values have to be excluded from the domain? -3, yeah. I set x plus 3 equal to 0. I have to make sure that doesn't happen. X equals -3 is excluded from the domain. If you put a -3 in, you'll get 0 in the denominator. Not allowed. All right, so part B here, I want to reduce this to lowest terms. So x squared minus 9, does that factor? Yeah. X plus 3, x minus 3 over x plus 3. And then what do you notice about this fraction now? You can cancel the x plus 3's. So this is just x minus 3. What does the graph of x minus 3 look like? What shifted 3 to the left? It's just a line. Yeah, that's got the form mx plus b, right? Yep. It's a line that has a y-intercept of -3 and a slope of 1. So y-intercept of -3, slope of 1 means that it would cross at 3. So something like this. -3, slope of 1. But what's the problem? Go back to part A. What has to be excluded? -3. X equals -3 has to be excluded. But when I graphed it, -3, it looks like it's on the line, right? But I have to make sure to exclude it, so I'm going to put a hole there. So -3, -6. So the spot where my domain said you cannot put -3 into this function, we have to put a hole. Okay, so the reason we had a hole and not a vertical asymptote was because the x plus 3 is canceled. So that is a common thing that happens, that always happens when you cancel something from the top and the bottom, right? That means you could not have plugged -3 in because you get a 0 in the denominator. And then when you cancel it, it ends up being a hole rather than an asymptote. So here's our summary. X values that make a denominator equal to 0 can result in either a vertical asymptote or a hole in the graph. Those are two ways you can have the function be undefined at an x value. You get a vertical asymptote if that x value makes the denominator and not the numerator equal to 0. You get a hole if that x value makes both the denominator and the numerator 0. This last scenario happens when you factor and cancel. You get the hole. Okay, so let's talk about end behavior of a rational function. The end behavior determines whether or if we have a horizontal asymptote. Where or if we have a horizontal asymptote. All right, so let's think about the end behavior of a few rational functions, see if we can draw some conclusions from these examples. So f of x equals 9x squared over 3x squared plus 1. So I have a picture of it so you can kind of see what the end behavior is from the graph, but if I want to think about it algebraically. So end behavior means what happens to the y values when the x values get really, really, really big, right? So think about plugging in like 15 quadrillion, right? The biggest number you can possibly imagine. Does that +1 in the denominator make a very big difference? No. So if I'm plugging in giant, giant numbers, I could say that it's approximately equal to 9x squared over 3x squared. Right? So this is kind of a fuzzy argument, but when your numbers are so big that you can't even conceive of how big they are, doing +1 is kind of like silly. It's just so small You can't even tell that it makes a difference. So this, when x is really, really big, we are approximately equal to 9x squared over 3x squared. And then the x squareds can cancel, and you get 9 over 3, which is 3. Right? So when x gets really, really big, y's are approximately 3. So see what happens with the graph. When x goes really far to the right, my y values are approaching 3. Yeah, they never get there. They're approaching 3. No, nope. They're getting closer and closer and closer, but they never touch or cross. And the same thing happens when I put in really large negative numbers into this function, because when you square a negative number, it becomes positive. So the same thing happens when you go to the far left. And you approach 3 from both sides. Okay, so the way I write this with my end behavior notation is as x approaches infinity, f of x approaches 3. As x approaches negative infinity, f of x approaches 3. All right, let's do a similar argument for the function g. Plugging in the largest x value you can, right? Plug in a Google, right? The largest number. Okay, Google I think is 1 to 10 to the 100. 10 to the 100, yeah, 1 with 100 zeros. So huge, huge, huge number putting in for x. That plus 1 in the denominator is so minuscule it hardly means anything. So this is going to be approximately equal to 9x over 3x squared. As long as x is really, really big, that plus 1 doesn't really matter very much. And then when you reduce that fraction, you end up with 3 over x. Right? What happens to 3 over x when x gets really, really, really big? It goes to 0. It gets really, really small. So 3 divided by 10, 3 divided by 100, 3 divided by 1,000, 3 divided by a trillion. Really, really small. So as x approaches infinity, f of x approaches 0. And when x approaches negative infinity, 3 over x is still going to approach 0. It's just going to approach 0 through negative numbers. So as I go to the right, my graph approaches 0 through positives. And from when I go to the left, the graph approaches 0, but up from the negative numbers. You can if you want, but I don't really require you to. You could put plus and minus right there if you want. Yeah. So because we're talking about end behavior, which means what happens at the very far ends, right? What happens when x is really big? Yeah. So yeah, this is only allowed when you're trying to figure out end behavior. Yeah. All right, one more example. I've got 9x cubed over 3x squared plus 1. Again, the plus 1 is so tiny, it doesn't matter. So I have 9x cubed over 3x squared. And when I reduce that, I get 3x. What happens to 3 times x when x gets really, really, really big? Yeah, yep. Y is going to get really, really big, right? If you plug in a big, big, big number for x, 3 times a big, big number is a big, big, bigger number. So that's going to go to infinity. And if you plug in a really big but negative number, 3 times a negative number is another negative, really negative number. So we go to negative infinity. So these are basically our only 3 possibilities, right? You could have an asymptote at a constant value, like 3. That happens, the reason that worked out to be a constant is because the degree on the numerator and the denominator were the same. So I was able to cancel the x squareds. And then you just got the coefficients, the 9 over the 3, ended up being my asymptote. In this example, I got 0. Okay, that's the other option. I could get a constant or I could get 0. You get 0 in this example because the degree of the denominator is bigger than that of the numerator. So after I did my reducing, I was left with a x in the denominator, which makes the whole fraction go to 0. And in the third example, the degree of my numerator was bigger than my denominator. So after I reduced, I still had an x in the numerator, which made everything just blow up. No asymptotes. So those are the rules of how you find asymptotes. You compare the degrees, but you can always do an argument like we just did, right? You don't have to remember the rules. You can just think about what happens when x gets really big. What happens when x goes to negative infinity? Okay, so some facts about horizontal and vertical asymptotes. A rational function may have several vertical asymptotes, but it can have at most one horizontal asymptote. So it can have none or one horizontal asymptote. A graph can never intersect, can never touch a vertical asymptote, but it can cross a horizontal asymptote. Okay, horizontal asymptotes only govern end behavior, what happens at the very ends. So in the middle, your graph could cross the horizontal asymptote. So here are some steps to how to graph a rational function if it's not a transformation of 1 over x or 1 over x squared. Because if it's a transformation of one of those two, you can just move the parent around as needed. Okay, but if it's not, follow these steps. Reduce it fully. You can check for symmetry, because if it has some symmetry, you only have to graph half of it, and then you can just copy the other half. Find the y-intercept, find the x-intercepts, find vertical asymptotes, find horizontal asymptotes. Plot at least one point between and beyond each x-intercept and vertical asymptote. And then connect all your points using your asymptotes and the symmetry as a guide. So we'll do an example together. All right, I want to graph 2x squared over x squared minus 9. So step one was make sure this thing is fully reduced. So I'm going to do as much factoring as I can. Okay, so f of x is 2x squared over x squared minus 9 factors to x plus 3, x minus 3. Anything cancel? No. So that tells me I have no holes, right? Nothing cancels, no holes. Now I want to check and see if there's any symmetry. Okay, so I want to evaluate f of negative x. If I put a negative x into that function, I get 2 times negative x squared over negative x squared minus 9. What's negative x quantity squared? X squared, yeah, because it means negative x times negative x, which is x squared. So I have 2x squared over x squared minus 9. Does that formula look familiar? It's exactly what I started with, right? It's f of x. What kind of symmetry do you have if f of negative x is the same as f of positive x? Y-axis symmetry, yep. Okay, so that's handy because now I'm only going to have to work on how to draw half of this graph. All right, let's go back and see. Step 3 was find the y-intercept and then the x-intercepts. Oh, I don't have very much room here. Y-intercept. So in general, for any kind of function, to find a y-intercept, you make what 0? X. Make the x 0. So I'm going to have 2. This is f of 0. 2 times 0 squared over 0 squared minus 9. And you get, nope. Nope. You get 0 over negative 9, which is 0. Okay, so I have a y-intercept at 0. X-intercepts. In general, to find x-intercepts, you make what 0? Y. So I'm going to have 0 equals 2x squared over x squared minus 9, and I want to solve for x. A handy shortcut when you're dealing with rational functions is that there's only one possible way the value of a fraction can be 0. What is that? The numerator has to be 0. To make the whole thing equal to 0, 0 divided by anything will give you 0. So the only way to make the value of a fraction be 0 is if its numerator is 0. So I don't even have to think about the denominator. 0 equals 2x squared. Or if that's hard to wrap your brain around, just imagine you multiplied both sides of this equation by x squared minus 9. So on the right, they'll cancel, and then 0 times x squared minus 9 is x squared minus 9. All right, what's the solution to that? X equals 0. It's the only solution. So that's my x-intercept is at 0. So I just have the origin, yep. Then vertical, then horizontal asymptotes, okay. So this was 3, 4, 5 vertical asymptotes. So to find vertical asymptotes, we worked on that last class. You set the denominator equal to 0. So we set x squared minus 9 equal to 0. And when you solve that, you get x squared equals 9, which means x is what? Or, yeah, plus or minus 3. So there are my vertical asymptotes. I can draw those in now. So I have my origin, which is my x-intercept and my y-intercept. Then I have vertical asymptotes at 3 and at -3. Okay, my next step is horizontal asymptotes, also known as end behavior. So 2x squared over x squared minus 9. There's two ways we can think about it. We could just think about end behavior and say, what happens when you plug in really, really big values for x? Well, when we're talking a Google squared, that number is so big that taking 9 away from it is like taking 9 grains of sand off the beach, right? You can't even tell the difference. So this is approximately equal to 2x squared over x squared, as long as x is really, really big. And then your x squareds cancel and you get 2. So y equals 2 is my horizontal asymptote. So I go up here and I put in at y equals 2. And actually, because it only governs end behavior, I'm not even going to draw it in the middle. Okay, then the last thing is to plot some points. Okay, so I've got all my asymptotes and all my intercepts. Now I just have to figure out how to draw the finished product. I need a few points to help me. So in between each vertical asymptote and intercept, I need 1 point. And then once I have that point, I'll sort of know how to connect everything. Because I have a couple of options. Vertical asymptotes means my graph approaches it. But I don't know, at this point, I don't know if it goes like this or if it goes like this. If I had 1 point, I would know which way it goes. So pick a value between 0 and 3. 2. Okay. So I'm going to figure out what the value of my function is when x is 2. Okay, so I'm going to do f of 2. So 2 times 2 squared over 2 squared minus 9. That's 4 times 2 is 8. 4 minus 9 is -5. Which is like -1 point something, right? -1.6. Okay. All right. So I can plot the point 2 comma -1.6. It's like about right there. And now I know everything that happens between 0 and 2, or between 0 and 3, because I now know my graph is heading down, and it has to approach my asymptote, so it's got to do this. What do you mean? Great question. Okay, so I think I know what you're asking. I'm going to draw it in a different color. Does the other half of my graph go like this, or does it go like this? Is that what you're asking? Yeah. Can we answer that right now? What do you think, Lex? Yeah, it's got y-axis symmetry because it's an even function. Yeah, yeah. So it's got y-axis symmetry. We looked at the symmetry as step 2. We said it has y-axis symmetry. So the other half has to be the mirror image over the y-axis. So it has to go down in the same way that the right half headed down. No, not necessarily. Yep. Mm-hmm. If I had had an origin symmetry, right? If I, in step 2, if I got origin symmetry, it would have gone up. All right, so now I just need to know what happens over here at the right, and then what on the left will be the same because it has y-axis symmetry. So after 3 is what I'm curious about. I know the end behavior is going to approach 2, but does it approach 2 from the below, right? It could look like this, or it could look like this, right? Because it has to approach the asymptote at 3 and the asymptote at y equals 2. So does it come from above or does it come from below? So let's plot 1 point. Pick a value bigger than 3. 5. Good. Thank you for not picking too crazy a number. Okay, so I'm going to evaluate f of 5. So I have 2 times 5 squared over 5 squared minus 9. So it's 25 times 2 is 50 over 25 minus 9, which is 16. Yeah. So 50 over 16, somebody give me an approximation. 3.125. That's actually equal, right? Okay. So I have 5 comma 3.125. So plot that point. 5 comma 3 in a little bit. So I now know that my function has to approach the asymptote as I go to the right. So it's got to come down like that. And I have a vertical asymptote here, which my graph has to approach. So I can draw that in. Yeah, rational functions have different looking graphs. Yep. All right, and then I have the same thing that happens on the left because of my y-axis symmetry, right? So the point -5, 3.125 is on my graph. I know from the end behavior that it's got to come down to my asymptote at 2. And I know I have this vertical asymptote that it has to approach. And there's my graph. Yeah, sure. I think I have some examples later in the lesson, but think of pollution in a lake, right? The maximum a lake could ever be polluted is 100%, right? 100% polluted. So you would have a horizontal asymptote at 1 to represent 100% polluted, right? And we could probably write some kind of function, a rational function where pollution's going in, pollution's coming out, and you have a ratio of the two. Yeah, yeah, yeah. I think we've got some examples later for real life stuff. Yeah, yeah. Mm-hmm. Yeah. Oh, no, not necessarily. Um, no, not necessarily. Yeah. Yeah, because we know, all we know is the end behavior and the behavior near the asymptote. It can look kind of warped in the middle there, but we're just drawing a rough sketch. Yeah. 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 All right, let's look at our next example. We'll do, I think we have one more together. Yeah. One more together, and then I'll let you try some. Okay. Okay, I have 4x over x squared minus 1. Step 1 was make sure everything's reduced as much as possible. So f of x, I want to factor, and if possible, cancel. So I have 4x over x squared minus 1 factors to x plus 1, x minus 1. Anything cancel? No, so I have no holes. Holes only happen if you cancel something. All right, step 2 is to look at symmetry. So I'm going to plug in a negative x. That's how you start for all symmetry questions. Plug in f of negative x. So I have 4 times negative x over negative x squared minus 1. Simplify, 4 times negative x is negative 4x. Negative x squared is x squared minus 1. Okay. Is that exactly the same as the function I started with? No, so we know there is not any y-axis symmetry. Is it exactly the opposite of the function I started with? Yeah, because when you have a negative in a fraction, you can put that negative in the numerator or the denominator or in front of the whole fraction. So this is actually negative 4x over x squared minus 1. That is exactly the opposite of what I started with. This is negative f of x. What kind of symmetry do you have if f of negative x equals negative f of x? Nope. Origin or odd symmetry, yeah. Cool, I'm glad you said that. X-axis symmetry. There's a little aside here. Here's a picture of a graph that has x-axis symmetry, right? What's wrong with that picture? Yep, each x has 2 values. So to have x-axis symmetry, it can't be a function because it doesn't pass the vertical line test. Good. Okay, so we've got origin symmetry. That's good. So step 3 was intercepts, right? Start with the y-intercept. Plug in 0 for x. F of 0 would give me 4 times 0 over 0 squared minus 1. What do you get? Nope, 0. 0 over anything is 0. For x-intercept, you set your function equal to 0, but a fraction can only equal 0 if its numerator is 0. So all I have to set equal to 0 is 4x. Just set the numerator equal to 0. And you get x equals 0. So my y-intercept and my x-intercept are both the origin again. Yeah, and if you have origin symmetry, it's got to go through the origin. Yeah. So we know the origin's a point on the graph. Okay, step 5, vertical asymptotes. So vertical asymptotes you get by setting the denominator equal to 0. So x squared equals 1. So you get plus or minus 1. All right, so I'm going to graph those. X equals plus or minus 1, vertical asymptotes. Okay. Okay, next step, horizontal asymptotes, also known as end behavior. So my function is 4x squared. Nope, it's just 4x, sorry. 4x over x squared minus 1. Think about what happens when you plug in a really, really, really big number for x. That minus 1 hardly matters at all. Okay, so this is going to be approximately 4x over x squared. You cancel an x and you get 4 over x. What happens to 4 over x when x gets really, really, really big? Gets really small. Yep. So my end behavior, this goes to 0. So my end behavior is the line y equals 0. It's going to be my horizontal asymptote. So I'm going to put that in, which is just the x-axis. Now I have to plot some points. So now I have all my guidelines in place. I just have to plot a few points. So let's see what happens between 0 and 1. I got to know, does my graph, it starts at 0 here, does it shoot up towards my asymptote or does it shoot down towards my asymptote? So pick a number between 0 and 1. 1/2. So let's plug 1/2 into my function. So f of 1/2, that would be 4 times 1/2 over 1/2 squared minus 1. So that's 2 over, what's 1/2 squared? Close. 0.25. Yeah, it's 1/4. 1/4 minus 1 is -3/4. How do I simplify that? I guess I could just use my calculator. 2 divided by -0.75. Or I could flip and multiply. I could say that's the same as 2 over 1 times 4 over -3. Right? Dividing by a fraction is the same as multiplying by its reciprocal. So you get -8/3. -2.67 approximately. Okay. So f of 1/2 is almost -3, so I can plot that. F of 1/2 is -2 2/3. So I now know that my graph goes down towards the asymptote. That. And then because I have origin symmetry, what has to happen on the other side of, has to go up to have origin symmetry. So on the other side of 0, it shoots up to the asymptote because of the origin symmetry. Okay. All right, now let's see what happens after my vertical asymptote of 1. Give me a value bigger than 1. 2. Yep, 2 is a good one. So I'm going to evaluate f of 2. I get 4 times 2 over 2 squared minus 1, 8 over 3. which is 2 2/3 or 2.67. Okay. So 2 comma 2.67. 1, 2 2/3. There we go. And just by knowing that one point, because I have asymptotes that guide my end behavior and my behavior near 1, I can just draw what happens, where I approach the asymptote for my end behavior, and then I go up towards my vertical asymptote. And because I have origin symmetry, this point was 2 comma 2.67. What point has to be on the other side of the graph? -2, -2.67. Yep. Opposite x values have opposite y values with origin symmetry. So -2, -2 2/3, and then draw your graph the same way. Up towards the horizontal, down towards the vertical asymptote. All right. That's it. Just there were 2 examples. And now you have some practice with graphing. Yeah, that's a great question. Yeah, let's graph it in GeoGebra. GeoGebra. Okay, so I'm just going to graph y equals, you need parentheses around your numerator and your denominator. So I'm going to have 4x divided by x squared minus 1. And then if I just scale it a little bit, that's the graph that we got. Yeah. So you can definitely use GeoGebra or a graphing calculator to check your work.